Good morning. My name is Khaled Bali. I am Irrigation and Water Management Advisor with the University of California Cooperative Extension based at the UC Desert Research and Extension Center in Hallsville. And the title of my topic today is Surface Irrigation Management Under Drought. You know, there are three main irrigation methods in California, and they're surface irrigation, and sometimes they refer to it as flood irrigation. And then there is the sprinkler irrigation and the drip irrigation. And we're going to focus today on the surface irrigation. And basically, there are three types of irrigation methods within the surface irrigation. That's border strip or flat irrigation. And typically, it has a slope of anywhere from a foot to about 2 feet and 1,000 feet. Furrow irrigation, which is a similar slope, and that's mainly for row crops like cotton, sometimes on alfalfa, sugar beets, and typically on vegetable crops. And basin irrigation, which is basically flat or zero slope. You know, we're not going to talk much about sprinkler irrigation or drip irrigation. There are completely two different methods of irrigation that typically require energy to pressurize the irrigation water. When we look at California, we have so many different crops. One of the big crops that we have is alfalfa. It's grown on about 1 million acres or so in California. So, you know, alfalfa would be a good example for surface irrigation or flood irrigation. And it's a primary method for most of the alfalfa and other field crops in California. So what is surface irrigation? Surface irrigation is basically the application method where water is applied over the soil surface by gravity. So there is no energy involved. It's the most common irrigation system in California and throughout the world. It has been for many thousands of years. So what happened over the last century, land leveling became a common practice, and that greatly improved the efficiency of surface irrigation. And like I mentioned earlier, this is a simple form of irrigation that requires no energy, just the gravity to advance the water in the field. So when we talk about surface irrigation, basically we're applying water to the field, you know, to the soil profile. And where this water goes, basically, we would like most of that water to go to the root zone storage. That's where that water can be used by the crop. Now, with any irrigation system, we're going to have inefficiencies or losses. And with the surface irrigation, the losses are mainly runoff. That's whatever water ends at the end of the field and doesn't stay in the root zone. And deep percolation, which is basically the water that goes below the root zone. So if we take a look here at this graph, and like let's say this is the beginning of the field, we're going all the way to the end of the field right here. And whenever we start the irrigation, we start at the end of the field. That's where the higher elevation, and the water advances just by gravity. So as you can see, we're going to have differences in irrigation time. Like let's say if we start at 7 o'clock in the morning, and it takes about 3 hours for the water to make it toward the end of the field, we're going to have higher irrigation time toward the beginning of the field compared to the end of the field. And then if we look at the moisture distribution below the soil profile, we're going to see something like this, where more infiltration at the beginning of the field compared to the end of the field. So with this type of irrigation system, we're going to always have the losses, which are surface runoff and deep percolation. Now we can talk about efficiency, how we can improve the efficiency of surface irrigation system. Again here, you know, the root zone storage, it's basically what's used by crop. And we typically use the term evapotranspiration to designate the amount of water that lost to evapotranspiration or crop production. And then we have the deep percolation and the runoff. So if we want to talk about efficiency, basically we want to maximize A compared to to B and C. So when we talk about application efficiency, It's basically A, the evapotranspiration, divided by the entire amount of water that we apply to the soil profile. So to improve efficiency or have higher application efficiency, we need to reduce both deep percolation and surface runoff. But there is a question here, if we're dealing with relatively clean or low salinity irrigation water, we don't need to worry too much about applying additional water because salinity is not a big concern. If we're irrigating with water that has high level of salts, we need to flush the salts from the root zone. So we need some percolation. Now we also need some runoff for uniformity. And so it's an acting balance. So sometimes we could have 100% application efficiency, which means we're under irrigating. We're not applying enough water to the entire field. So surface irrigation methods, we talked about border irrigation and sometimes called flat irrigation. And the runoff rate typically with this type of irrigation system vary from one location to another, vary depending on the length of the field, the amount of flow rate, the crop there. But just to give you an idea, it's anywhere from 5 to 20%. When we talk about furrow irrigation, and sometimes it's called bed irrigation, the runoff rate is typically higher. It's anywhere from 15 to 30%. So when we have runoff, if we're applying nutrients or pesticides, whatever water we lose at the end of the field, it's going to contain nutrients and pesticides. With deep percolation, we're going to have mostly nutrient losses, especially nitrogen. Now with basin irrigation, typically basin irrigation is a flat, zero slope, so we don't allow any runoff. And basin irrigation could be an efficient form of irrigation, but typically you have to have small runs compared to border and furrow irrigation. This is just to give you an idea about the amount of runoff. And also there's another concern in California here, water quality regulations. So we're looking here at the concentration of sediments or silt in runoff water. The blue line that you see here is the amount of runoff in terms of percentage from applied water. And as you can see here with this type of border irrigation, the runoff rate is typically not too bad. Here we're talking about 15% or so. When we look at the brown line here, which is sediments or silt, and that's in concentration of milligram per liter or parts per million, you can see also it's not too bad. It's about 150, maximum 200 parts per million. Now, when we look at the same exact soil type, but we're going the same crop with furrow irrigation here, you can see we have relatively higher runoff rate and higher concentration of sediments. So when we talk about management, we need to pay more attention when we're dealing with furrow irrigation on any crop, not just alfalfa. So what do we do when we have limited water supply, when in a situation like we have a drought and we don't have enough water to irrigate the crops that we have? Well, the key here is to reduce surface runoff and deep percolation. So how can we reduce surface runoff and deep percolation? We can apply less water and manage it carefully, and there are several methods that we're going to talk about, about how to do it in terms of management or in terms of system modification. Now, when we have limited amount of water, salinity buildup could be a significant factor, especially if the salinity of the irrigation water is high. So we may end up under irrigating and accumulating the salts in the soil profile. We also have to look at water quality. Do we have anything other than salinity that we need to be concerned of, like accumulation of chloride, for example, if it becomes toxic to the plant. Then when we go back to normal situation where we have enough water, we need to consider leaching. and we may have to apply additional water to remove the salt buildup in the soil profile. So water conservation, there are several ways that we can do water conservation. ET, soil-based irrigation scheduling, which is like we talked about evapotranspiration, that's ET. Irrigation management, looking at how much flow we have, how we can time the irrigation. Can we adjust the set time? Instead of having irrigating one border, can we irrigate 2 or 3? And ways to increase application efficiency or irrigation efficiency. So when we talk about irrigation water management, is basically determining and controlling the rate and amount and timing of the irrigation water that we apply to meet the crop water requirements. I'm just going to mention here, one of the relatively simple programs that we have, an Excel-based program, basic irrigation scheduling program developed by Rick Snyder from UC Davis, and this is the website for it. Rick is going to talk about this when he talks about irrigation scheduling. Just want to introduce the concept of CIMIS, California Irrigation Management Information System. And that's basically where we get the basic information about reference evapotranspiration and how we can relate this one to other crops. Just want to give you an example of evapotranspiration or reference evapotranspiration. This is down in Southern California, and you can see that evapotranspiration varies between summertime and wintertime. It's relatively high in summertime. It approaches like 12 inches a month or 10 millimeter a day in June or July. In wintertime, that number goes down to almost 25%. You can see like January and December, we're just talking about 3 inches a month. When we talk about irrigation scheduling, we need also talk about soil moisture measurements. There are a whole bunch of different devices that we can use that they can tell us how much moisture we have in the ground, and that will give us an idea how much water we need to apply and when the crop gets to the point where it's stressed. This is a picture of alfalfa right here. And this is a soil moisture measuring device that is with sensors through the soil profile, and basically gives us an idea about the soil moisture content. And when we get to a certain level, the crop will be stressed and it's time to irrigate. Sometimes we can estimate how much water we need when we irrigate, next time. They are a whole bunch of different methods, especially over the last 10 years. So I'm not going to talk about anything specific. Now, another way to improve irrigation efficiency is on-farm practices. One way we talked about runoff, and minimizing runoff would be a good way to increase efficiency. We could take that runoff and recycle it. We could use it on the same field, or we could send it to a field downstream from the end of the field that we're irrigating. We also need to look at ways to reduce deep percolation, but sometimes that is not practical. We could do, in some certain situations, water table control, manage the depth of water table, and this way we could also manage how much deep percolation that we have. It's hard to look at deep percolation because we can't see it. It's below the soil surface. This is an example of a tail water recovery system, which is basically on your left right here. It's a big ditch at the end of the field that we take all the runoff water collected in this ditch, and we can use it downstream to irrigate another field, or we can send it back and irrigate and recycle it on the same field. So that's a good way to conserve water. So all that runoff water is no longer lost, it's used on the farm. Tailwater recovery systems are really good in improving the quality of irrigation water, the quality of drainage water. So if we're applying pesticides or nutrients, we're no longer sending this runoff water to the drains. We're reusing it on the field and improving the efficiency of both the irrigation efficiency and improving the quality of drainage water. This is just to give you an idea about a typical irrigation system in Southern California. You know, this field right here is about 80 acres, and these are border strips. You know, they're about 200 feet wide by about 1,250 feet long. And so the irrigation starts from this end, and with whatever flow rate we have, we could irrigate one land or one border, or we could irrigate two. So we can manage the flow based on the circumstances that we have in the field. Now, once the water gets to the end of the field, that water could go to the drain, or in this situation, you know, it goes all the way down here to runoff recovery system, where we take this water and reuse it again on this field or any of the other four fields that you see in the picture. There is another way to improve efficiency by reducing runoff in terms of management. So we talked about system where we can use runoff recovery system. Now let's talk about management. You know, we developed a runoff reduction technique where, you know, an irrigator can determine how much, when it's time to turn the water off in order to get reduced amount of runoff. So in this example that I'm using here, I'm using the slide chart to come up with no more than 5% runoff, which is really good, which means that we have higher application efficiency. And in this technique, we only need a few things, just the flow rate, how much water we have in the irrigation ditch, and how fast the water is moving across the field. So for example, we could start the irrigation at 7 o'clock and come back 2 hours later, let's say 9 o'clock, and find out how far that water made it. So if it made it to 400 feet, I know it takes about 1 hour for the water to advance 200 feet. So the main output here is irrigation cutoff time, so we can have less runoff. And this could be accomplished in several ways. We have Excel programs or a handbook that could be used in the field, or the simplest one is a slide chart. And this is, we make them available in both English and Spanish. And this is just to give you an idea, an example of the irrigation cutoff time calculator. This works really good for clay soils, which basically, you know, it gives you, clay soils gives you uniform application, water application. So the irrigator can use this slide chart in the field and just take you know, flow rate measurement from a flume or any other water measuring device for flow rate, and the advance rate that we talked about earlier. And from this, you know, just a few manipulations of the different slides here, we can come up with cutoff time, so we have very little runoff. So this is a management. It doesn't require any modification of the system, but it requires extra time to do it. This is just to give you an idea. You know, we're interested also in water quality, and this is the phosphate in runoff water. And in this case, we have different treatments. And I just want you to look at this one. This is the type of phosphorus application where the phosphorus is applied to a crop like alfalfa. And we implemented a method of reduced runoff. You can see how much reduction we get in terms of the load of phosphorus in runoff water. So it's not only effective for conserving water, but it's also effective for meeting water quality criteria. And for the last few years, we've been doing lots of work on automation of surface irrigation systems. Like we mentioned earlier, we've been using surface irrigation for thousands of years. Automation of surface irrigation system is basically making all the irrigation variables and using them in a way where we can make a smart decision about how much water we apply and when we need to turn the water off. Surface irrigation is sometimes an art because you have to deal with so many different variables. For example, the flow rate. The flow rate could be constant. How fast the water is moving through the field. And that could also depend on the soil type. If we have light ground or sandy ground, we typically have lots of infiltration below the soil surface. If we have heavier ground, we would have less infiltration rate and the water will advance faster. It also depends on the crop. Like if we're doing a germination irrigation on wheat, for example, the crop is just basically germinating and there is not much resistance for the water as it moves through the field. So automation is a smart decision based on accurate and real-time data looking at all these variables. And irrigators typically, they make decisions based on their experience combining all these factors together. So basically with automation, this is, just to give you an idea, this is the beginning of the field, this is the end of the field right here. So whenever we're doing applying water with surface irrigation, we have water that infiltrating during the irrigation event, and we have water above the soil surface. So what we try to do is to turn the water off at some point before it reaches the end of the field, where we can have all this surface water above the surface comes down and infiltrate at the lower end of the field, as you can see here in this graphic. So basically, we would like to have very little runoff, and we could accomplish this by taking into consideration all the irrigation variables in the field. So optimization, which is the same thing as automation, is just adjust the irrigation time to allow for changing crop roughness, for example, changes in flow rate, changes in field conditions. If you have an alfalfa and we're doing the first irrigation after cutting, so we have relatively small crop. If we're doing a second irrigation after cutting, we're relatively a higher crop, so more resistance. Now this is all, we can take all these variables and do some relatively simple simulation in the computer and determine when we need to turn the water off so we can have very little runoff. This is just to give you an idea about one of the variables, soil type. So this is right here is about a 40-acre field. And as you can see in the picture, there are 3 different soil types. So typically, our recommendation, the standard recommendation would say, if you have a sandy field, to improve irrigation efficiency and reduce runoff, cut that field in half. So you don't have too much variation in irrigation time between the beginning of the field and the end of the field. In this situation, if we use automation, we can adjust the flow rate based on the soil conditions that we have. So if we start here with heavy soil, we may have start with a lower flow rate. Basically, maybe we're irrigating 2 borders. The minute we move to the center of the picture right here, to the light ground, we may use the same flow rate to irrigate 1 border. So we have higher advance rate and less variability between the irrigation time at the beginning of the field and at the end of the field. So as you can see, this is what we can accomplish with automation. Sometimes we could use existing gate structure, as you can see here to your left. This is a typical 14-inch gate, and we have a simple automated gates that could be run by a smartphone or just by a remote controller or switch by an irrigator. So the level of sophistication is there. And this is another example using an existing ditch where we don't make any modification to the irrigation canal. On the right-hand side here, we decided to make modification to the ditch so we can have more control. So as you can see here, this is the beginning where we made the modification to the ditch. Down here, we installed an automated gate that can handle flow rate ranging from like 3 CFS all the way to 15 CFS. And this could be done based on the conditions that we have in the field, so we can improve irrigation efficiency. As I mentioned, this could be done smart irrigation controlled by from a smartphone, or it could be as simple as going there and just with a remote control turning it on and off. We also need to see how fast the water is moving across the field, and right here it's hard to see, but that's an advanced sensor which is basically tells us how fast is the water moving across the field. So in summary, tailwater recovery systems can save water. We need to be careful if we're dealing with irrigation water that has a high salinity. We may have issues with temperature, especially in summertime, as the runoff water goes above the soil surface, it picks up temperature. So if we reuse it right away, we may be irrigating with the water that has higher temperature and higher salinity. Irrigation management and irrigation scheduling are key factors for water conservation. We did not talk much about irrigation scheduling because this is the topic of another drought management seminar. And we talked about irrigation management. We could do irrigation management by keeping the existing system and just investing a little bit more time to improve the irrigation efficiency. Or we could do modification to the irrigation system, like runoff recovery systems, or having automated gates. Automated irrigation, there is a potential that it could save water and reduce labor cost. Surface irrigation takes lots of labor. So a typical 80-acre field would require maybe 24 hours to irrigate. With automated irrigation, we could reduce the amount of labor by almost 75%. And again, we're in California, and in some areas, salinity is relatively high. So we need to pay attention to salinity and salt buildup in the soil profile. So if we have a situation where we're irrigating with high salinity water and we ended up under irrigating during a drought or when water is not available, we need to pay attention and add additional water later on so we can bring the soil back to original condition. And thank you.